Why is the screen blank? Oh, no, it is working. Okay. Cool. There have been some more, or well, it's the same request for problems to go through, but different problems. I'm going to copy them. I think it's only these two that I didn't look at last time. Not sure what year they're from. Let me just check if there's any other problems. Actually, I do want to talk about the in circle, X circle thing a bit more as well, because there's some interesting things to say about that. Ah, hello, I see you have joined. Okay. Last time, is this loud enough and so on? Last time with the in circle, X circle thing, I made a big point that you can get it by considering areas of some triangles and then couldn't figure out which triangles I wanted to consider. And I did, while falling asleep yesterday, realize how it works. So we managed to show last time that, okay, so here's the angle bisector, and both of the X center and the in center are on this line, and if you then draw the radius there that's perpendicular to that tangent, and that one, artist's impression of perpendicular lines, then if we called this length x, x, y, y, and z, z, then we realize this length is y, and we got that, let's call this r and ra, and you get that r over ra is x over x plus y plus z. And r times x plus y plus z is famously the area of this triangle over here. What am I doing? Okay. And so this suggests that RA times X should also be the area of this triangle. And now the question is, why is RA times X the area of this triangle? And the problem is, if you're trying to imagine it as a triangle somehow involving this side length and this side length, you're not going to get very far. The thing that you actually need to consider to get this to work, let's call this B and this C, is that X is a half of B plus C minus A. And so the way to get this as this relation from considering areas of triangles is actually not as one area, but as the sum of two areas minus a third one. So let's see how this works. So there's two ingredients we need here. And one of them is we're going to prove that R times, well, half of the in radius times A plus B plus C. So R times the so-called semi-perimeter is the area of the triangle. Triangle. And the reason why this works, so here's the in center and here's our in circle. So we draw these. Yes, I'm proving. I'm doing it differently this time because I mentioned there's a way to do it with areas of triangles. So the one formula we do need is this formula for the area of the triangle in terms of the in radius. So the way that this is going to work is actually we want to break the triangle up into three smaller triangles. Okay, so let's give these side lengths some names. A, B, C, and the in radius is R. So we've got the blue triangle, this green triangle, and let's make it orange, the orange triangle. Okay. And the area of the blue triangle is a half of R times C. Is a half of RC. And the area of the green triangle is a half of RA. Oh, you learned this yesterday. Cool. Okay. So half of RA. And then the orange one It's an interesting thing to be aware of. It is a very famous formula for the area of the triangle, given the in radius and the so-called semi-perimeter. And so if you add these together, oh, I see. If you add these together, you get that the area of the whole triangle is just the blue triangle plus the green triangle plus the orange triangle. And so that's going to be a half of r times a plus b plus c. And you'll sometimes see this written as r times s, where s is defined to be a half of abc. And s here stands for semi-perimeter. Semi meaning half, and perimeter being, well, perimeter. Or outside measure, I guess, is technically what the individual parts of the word means. So now with the X circle, this is what we're going to do. Okay, so here's our triangle again. And let's give this some names. So we call this side, this vertex A. And here's the, okay. Okay, not very good, but let's pretend that it actually is tangent over there, like it should be, and over there. And over there, as you can see, these lines look very perpendicular. And so this side is A, and let's call this B and C. And so we're again going to work out the area of this triangle, but this time how we're going to do it is in terms of, we're going to take, let's make it blue, green, and or let's make it purple since I've already used blue. So we're going to actually take this purple triangle, okay, and we're going to call this length here the X radius opposite A. And let's take this green triangle. This is definitely a straight line over here, or it's supposed to be at least. And then we're going to subtract. Oh wait, how does... I thought I could just subtract this triangle, but that's not going to give me what I want actually. So it's not this purple triangle, it is... Okay, let's use the right triangle, or this is not going to work. We want this purple triangle, but its height is still RA. And we don't want this green triangle. We want this green triangle and this orange one. Okay. And you're going to see that the area of the triangle itself, this black triangle over here, is going to be the purple one plus the green one minus the orange one. Because then you're adding, you're adding this whole thing, but removing this piece. So the height here, so we're going to use B as the base. And then the height is then the line that's perpendicular to this side and goes through the other vertex. So it's this, this length over here, which is RA. And for this one as well, we're going to use this as the base. And the height is the line that's perpendicular to that side and goes through the other vertex, which is also RA. And then for the orange triangle, we've got here as the height is RA. And so the area of purple, is a half of B times RA. And the area of green is a half of C times RA. And the area of orange is a half of A times RA. And so you get that the area of the triangle is going to be purple plus green minus orange. So the area is a half of RA times B plus C minus A. And so what you then get, the conclusion that you're able to draw, is we saw that the areas simultaneously are half of little r, the in radius, times a plus b plus c, but it's also a half of the x radius times b plus c minus a. And so you get the same formula, r over ra is b plus c minus a over a plus b plus c. And if you rewrite these in terms of the little x, y, and z that we had before, you get the same formula that we got by looking at the similar triangles. It's just now with considering area instead of similar triangles. So maybe this is a more complicated way to do it, but this is the thing I was talking about where you can do it just with looking at areas of triangles. And so again, if you add them, r over ra plus r over rb plus r over rc is equal to b plus c minus a over a plus b plus c plus c plus a minus b over a plus b plus c plus a plus b minus c over a plus b plus c. And again, you're going to get that this is equal to 1 because it's going to add up to a plus b, or 2 times a plus b plus c minus a plus b plus c. So just a plus b plus c over a plus b plus c. And so you get the same conclusion as last time, just with a different proof. And you get this nice formula for the area of the triangle in terms of the x radius and the sides of the triangle. Also, with this question specifically, potentially a way to approach it without knowing the formula. But this does still require you to know that this length is equal to this length over here. And that will still require you to know that this length is equal, or you'll have to calculate those lengths for this other approach that I've thought about. What we can also do is if we draw this triangle, so it turns out there's a triangle there that go like these points here and this vertex of the triangle actually lie on a straight line, because the straight line that I'm drawing here is the so-called external angle bisector of the triangle. And you can work out what these lengths are because we know what this radius is and we know what this length is, so we can work out this piece. And we don't know what this radius is. This is what we're trying to work out. But we do know, we might know this length and so on. And so the alternative way to do it maybe is you can calculate that this angle over here is 45 degrees and then use some trigonometry and set up an equation. All in all, the question is very annoying, but it is potentially doable, but you will also, it still relies on you being able to calculate that length over there, which, I mean, it's not too bad. There's probably some other approaches as well, but this is the other one that I managed to figure out. But anyway, let's look at the other two problems that you mentioned, or that you asked about. Okay. The annoying thing about the way that they phrased question 17 is they're relying on you knowing that there's a convention that when you have a triangle, that little a is the length opposite the vertex A, and little b is the length opposite the vertex B, and little c is the length opposite the vertex C. And that's like, they could have said explicitly that C is the hypotenuse and not left you, like, left no doubt about what they ask, or not hypotenuse in this case, because it's a right angle triangle. Anyway, in triangle ABC, we have that angle C is 90 degrees. So this is our setup. Yeah, okay, that is true. That is the normal convention, at least. So C is the 90 degrees, so this is C. Also, when you have right angle triangles, also, like the way that you usually see Pythagoras written is a squared plus b squared equals c squared. But it does annoy me a little bit that they don't say it explicitly, that they sort of, whatever. It's not that important, I guess. Anyway, we have A and B are not equal, so those angles are not 45 degrees. The numbers x and y are real, such that x over 2a squared plus y over c squared equals 1. X over 2a squared plus y over c squared equals 1. And x over c squared plus y over 2b squared over c squared plus y over 2b squared is also 1, I take it. Yeah, and I want to know what is x plus y if c is 3. So the triangle, I think the only important thing is the Pythagoras relationship over there, so that we know that a squared plus b squared equals c squared. And our goal is to calculate x plus y. Yeah, so like this is just a system of two linear equations, so you can just solve it. So let's multiply this whole thing by 2a squared c squared, I guess. So you've got c squared x plus 2a squared y equals 2a squared c squared. And you've got 2b squared x plus c squared y is 2b squared c squared. And I get, like, I mean, if you've got no other ideas for how to do it, which at the moment I don't, you could always just solve for x and y. So multiply this equation by c squared, this one by 2b squared, subtract them so that the x's cancel. You know, just solve it like a normal system of equations. I think we might be able to, it might be less horrible to, 2b squared plus c squared is going to relate to 2a squared plus c squared. How? It's not really. I don't know. I was going to say maybe we can just add them and like things just work out nicely, but doesn't look like it. I think the best approach I've got at the moment is just to solve this. So we've got 2b squared c squared x. So I'm multiplying the first one by 2b squared. So plus 4a squared b squared y is 4a squared b squared c squared. And the second one, if I multiply by c squared, I've got 2b squared c squared x plus c to the 4y is 2b squared c to the 4. And let's subtract the second one from the first one, I guess. So we've got 4a squared b squared minus c to the 4 y. I've got no better ideas, but there must be a better way to do this. 4a squared b squared c squared minus 2b squared c to the 4. So we could take out a 2b squared c squared, I guess, as a factor. 2b squared c squared. 2a squared minus c squared. That's annoying. This doesn't even, like, if there was a b squared over there as well. Whatever. Okay, sure. This came from taking this and multiplying by 2b squared. Yeah. This came from multiplying this by c squared. I'm doing that so that the x's have the same coefficient, so that when I subtract it, the x's cancel out. And so I've just got this minus this, which is this, times y, is this minus this. And then here you can take out a common factor of 2b squared c squared. And so then you're left with 2a squared over there and a c squared over there. And so you can work out, yeah, I mean, like, I'm not saying it's pretty. I'm just saying I've got no other ideas at the moment. So you could solve it this way. You can work out y explicitly as 2b squared c squared 2a squared minus c squared over 4a squared b squared minus c to the 4. And I'm guessing if you did the same thing with x, you're going to get something like x is equal to 2a squared c squared 2b squared minus c squared over 4a squared b squared minus c to the 4. I mean, we can probably double check that and actually solve the equations, but this is sort of just by symmetry, by swapping the roles of A and B, because these equations are the same except for switching A and B around. So that's why this is my guess for the value for x, is that you get the same thing just with A and B swapped around. And so if you add these, you're going to get, well, we've got the 4a squared b squared c squared, 4a squared b squared c squared. And then we're subtracting, well, let's work it out. X plus y is, come on, is going to be, so we've got 4a squared b squared c squared plus another 4, so 8a squared b squared c squared, and then we've got minus 2c to the 4 a squared plus b squared over 4a squared b squared minus c to the 4. And then the a squared plus b squared is just c squared, so actually this is now c squared, or let's make it 2c squared because I want to make it look like the denominator there, times 4a squared b squared minus c squared times another c squared, yeah, minus c to the 4 over 4a squared b squared minus c to the 4. Think, and then that's going to cancel with that, which is very convenient. And you just get 2c squared as the value of x plus y. Now it feels like there must be a better way to get that this is the value of x plus y, because that's a very clean answer. But yeah, if you like, yeah. But the first idea I had is just solve the equation, and that ends up working, but I feel like there must be a better way. 2c to the 4, and here we're going to get nah, I've got no ideas. Unless this equation like means something, like maybe it's the, I mean, this is the equation of a line, so maybe we could interpret this as, I don't know, which line. No, maybe the x and y is a interesting intersection point of two specific lines that are somehow related to this triangle. So this is the line where the x-intercept is at 2. Yeah, but like 2a squared is a random point way out here. And c squared is a random point way up here. So like I don't get what the significance of these lines are. Like why is this line interesting? I don't know. Yeah, I've got no better idea than just solving these equations, unfortunately. But fortunately, they're not that bad to solve. And everything does simplify nicely once you use Pythagoras over there. Cool. I think that works. But it doesn't leave me satisfied. It doesn't speak to my soul. And I guess like the actual answer for the question then is if c is equal to 3, then this is 18. Okay. In question 18, I'm actually just going to paste it again because I don't want to keep scrolling up to see the question. So the learners in grade 10 are divided into two groups. One group consists of 2m boys and 13 girls. Okay. And the other is 7 boys and 2n girls, with m and n are positive integers. Well, I would hope so. They ask a variation of what? Of this question 18 or of 17? I'm guessing 18. Each learner pays the same integer number of rands into a fund, and the total amount of money raised is that thing. What is the total number of rands paid by each learner? So, I mean, again, I've got no real ideas other than give this a name, like let's call it K. And so the total is going to be, well, K times 2m plus 13 plus 7 plus 2n, I guess, has to be 2mn plus 7m plus 13n plus 84. Well, that seems weird that this is actually enough information to determine this, but okay, whatever. We'll see where this goes. So 2k times m plus n plus 10 is 2mn plus 7m plus 13n plus 84. Nope. I mean, once I get to the answer, I'll realize what the trick is that I should have spotted all along. The thing about things like this is this can be factorized, like sort of. This is a half of 2m plus 13, 2n plus 7, and then minus, so 168, and here we've got 91. So actually I think we want plus 168 from 91 is 77. I don't know. Like that's the only thing that, like, the only other thing that immediately came to mind is that, like things that look like this can sometimes be broke, but like this doesn't seem important. Although it kind of is, because that 2m plus 13 is over there and that 2m plus 7 is over there. So if you've got something that looks like AMN plus BM plus CN plus something, so this is always 1 over, like, the easiest way to do this is you're going to have AM. If that A wasn't there, if you just had MN plus like BM plus CN plus CN, then here you'd have M plus CN plus B, I think, minus BC. Like it's a product of two linear factors like that. So it's the trick that you can use here is that we can end up with something like, I'll just show you how it works. Okay, this is 1 over A times this whole thing multiplied by A. So A squared MN plus ABM plus ACN plus AD. And so this is now 1 over A times AM AN plus something plus something. And then we want to work out what the somethings are. So now to get the correct thing for the N on its own, we need a C over here. And we need a B over here to get the M to work out correctly. But now we've got plus BC over here and we want AD. So this is plus AD minus BC. So basically it's a half of, I took this thing, so that gave me the half, so that I've got 2m and 2, so that I can use 2m and 2n in the factorization. And then this 13 is just this 13, and the 7 is just this 7. So it's like literally just the numbers from the coefficients from the original expression. And this A is like that A, and then this is just whatever you need to do to make the constant term come out correctly. So here we've got like 91, but we need it to be 168. And so I need another 77. Again, I don't know if this is actually helpful, but like I'm a little bit more convinced that it's helpful because we've got this, because these things show up there. Although maybe we can just make this work somehow. Okay, so we've got, oh, why do I have this page here? Again, let's paste this. I don't have to keep scrolling up. So I had k times 2m plus 13 plus 2n plus 7 equals a half of 2m plus 13, 2n plus 7 plus 77. So let's call this thing, I did not, okay, let's call this thing x and this thing y, just because I don't want to keep writing them out. So we've got k times x plus y is a half equals, come on, of xy plus 77. And I guess we actually get to the same thing here now. So we've got xy minus 2kx minus 2ky plus 77 is 0. So we can do the same factorizing trick. This is x minus 2k, y minus 2k plus 77 minus 4k squared equals 0. But this is, I don't think this is actually going to go anywhere though. Because this doesn't restrict anything that we're dealing with here. I was hoping for something where we just get like a fixed number over here so that we can just consider all of the factors, but here we've got this, I don't know, I don't see what to do. What was the x actually? X was 2m plus 13. And y was 2n plus 7. Nope, still not interesting. And if I multiply these things, I have to get that, but like, okay, cool. Not only do I not know the trick for how to do this, I don't even know how the not a trick way to do this. Okay, let's try the long way. Let's go back to, we have k times 2m plus 2n plus 20 has to be equal to 2mn plus 7m plus 13n plus 84. Was that the number? So I guess the other thing that we know from this is that 2m plus 2n plus 20 has to be a factor of 2mn. But we're going to like end up with the same thing. It's going to be the same like weird conclusion where Because I guess, yeah, this is always a factor of 2mn plus 2n squared plus 20n. And so we get that this must divides 2n squared plus minus 7m plus 7n plus 84. But like we haven't gotten rid of like the quadratic term here. We still have, because we're gonna be able to like make it a m squared or an n squared or an mn or whatever, but I don't know how to get rid of it completely. Mm. M plus n plus, because it would be nice if this was just, yeah. It's 4k squared minus 70. Yeah, that's not going to do anything interesting. Yeah, then we just get the mn back. So like, okay, what is the same number of rands into a fund? Total amount is that. What is the number? I have no idea. Well, okay. We can cheat. 86, 106, is that going to be a divisor? 24? It's not going to work. Like if we find values of m and n that work, and then work out what k is there, then that must be the answer, because, you know, this is the second round, so there's a fixed number that's the answer. So I guess, yeah, like just, although, I don't see what the constraints here are. We just need that, I was going to say, we just need that this is like a number, like we don't even have a lower or upper bound on what this number is. K can't be too much larger than m and n though, but like that's about it. I guess we need bigger than 77. I guess we need k is bigger than 5. 23. Like it is 1 times. Be 1. Yeah, it can be 1, and then that would have to be, I mean, I think that actually just works, but then why is that unique? Like if we go back to, with a lot of effort earlier, we got 2m plus 13 minus 2k times 2n plus 7 minus 2k is equal to 4k squared minus 77. And we just need this to be positive, so Like 4 times 4 squared is not big enough. That's only 64. But like if we make k like 5, no, we could just solve 2m plus 3. 2n minus 3 is equal to 4 times 25 minus 77 is 23. Like, I don't see what's wrong with, like, this has solutions. You can make this equal to 1 and this equal to 23. No, so that gives you m equals 10 and n equals 2. And like, that means k equals 5 is an option, but that doesn't feel like it should be unique. Although let's check that this actually works. So m is 10, n is 2. So I'm claiming that if we have 20 boys and 13 girls in the one class, and 7 boys and 4 girls in the other class, and they all collect 5 rand. Oh, they say any integer bigger. Oh, was this? But oh, so it's not unique. But then how did they ask this in a? Yeah, how would you put this in as an answer if the answers are all 3-digit numbers? In 2016, you say. I'm gonna go find it because then, yeah, how was this a question if it doesn't have a unique? Because I was like, I really could not see what's going to make this unique. 5 is the smallest because unless they messed up and thought it had a unique solution and then... Yeah, okay, so then what? Oh, to this problem. Oh. Okay, they say that they did mess it up. Oh, okay. That's how they messed it up. Yeah, so they say they just didn't count this question. So it's like, yeah, how? Because like as long as you get a positive number on this side, you can just make this number equal to 1 and this number equal to this thing, and you get a solution for every k. Because like if you make 2n, I'm making this one 1 because this is the smaller one of, or not the smaller, but it's the one that's like when k is 5 or more, you've got 2n minus something, and here you've got 2m. You might also have minus something over here, whatever, but like let's make this one 2n plus 7 minus 2k equals 1, and 2m plus 13 minus 2k is 4k squared minus 77. And that is just going to work out. Like, this just gives you that m is 4k squared plus 2k minus 77 minus another 13 is minus 90. Divided by 2. K minus 45. And n is k minus 3. And that just is a solution every time. I don't know if there's a trick for this, like other than this factorizing thing that we did here. Like whenever you have questions that are, mn plus something times m plus something times n plus something equals whatever, then it's usually you're going to try to factorize this as m plus something, n plus something equals some number, and then this number's got like a finite list of factors, so you just try all of them. But cool. Okay, so they messed up that question. Okay, can we try this one? Let's copy it. A certain card shuffling machine always rearranges cards in the same way. Well, then it's not a very good shuffling machine. If 13 playing cards are inserted in the normal order, then it goes 6A, 7, 4, 2, 9, KJ, 10Q, 853. What is the least number of times that the cards can be fed through the machine to get back to the original order? Again, surprised that they asking this kind of thing in Samo round 2. More similar to what we're doing right now. So not this one, but I will go back to this one because there is a way to work this out, because you can just work out what this permutation is and then get the lengths of the cycles in the permutation and then take the least common multiple of them. But again, that's surprising that they put that in the round 2, because like I've sat in the committee room when they're setting these papers and they are very determined to have stuff that's actually in the high school syllabus. So, okay. 300 white boxes and red boxes in storage. Each box contains the same number of soccer balls. I'm having lots of arguments with people about whether it's soccer or football. Apparently, even though the word soccer comes from the UK because it's like short for association football, people in the UK tend to call it football now and think of soccer as the American word for it. And so this is one of the rare, very, very rare cases where I agree with the Americans. Each box contains the same number of soccer balls. The total number of soccer balls in all the boxes is this, determine n. Okay, so we've got 300 white and n red boxes. So we've got 300, 100 plus n is the number of boxes. And this must be a factor of n squared plus 290n minus 2490. And yeah, that's going to be enough to solve this. So the way to do this in general, n plus 300 divides n squared plus 290n minus 2490 is, well, essentially going to do polynomial long division. So you're going to divide this by this, and you're going to get a quotient and a remainder, and this has to divide the remainder. But if you want to, you can also think of it as, I'm going to try to, well, it's the same procedure. This thing divides n squared plus 300n, always. Right? And so it must divide the difference of these things. So it's going to divide 10n plus 2490. And then I'm going to try to get the n's to match up so that I can get rid of the n, so that I just get that this divides some numbers. So this always divides 10n plus 3000. And so it divides the difference of these two things, which is then 510. Or if you remember what we were talking about on Thursday with the polynomial long division, you've got that n squared plus 290n minus 2490 is going to be n plus 300 times n minus 10. And that's going to be minus 3000, so plus 510 is basically the idea. Yeah, okay, so it's the same procedure, plus 290n minus 2490. And we're going to divide this by n plus 300. And so we want to make, we go term by term and try to make the coefficients match up so that when we subtract it, this cancels out. So I need to multiply this by n to get an n squared. And so I get n squared plus 300n. Now I subtract these and I get minus 10n minus 2490. question again. So then I want to make these coefficients match up so that when I subtract them, this cancels out and I get something with a smaller degree. And so if I have a minus 10 over here, I'm going to get minus 10n minus 3000. And then when I subtract these, I'm just left with 510 as the remainder. And so you get this thing. And so that means that if this is divisible by n plus 300, well, this part here on its own is divisible by n plus 300. So this part here also has to be divisible by n plus 300. So it's the same sort of thing. I'm saying if this divides this thing, well, it also divides this thing, and I've gotten this by trying to make these coefficients match up so that then when I subtract them, I get something with smaller degree. And then now with the division, it's I'm actually not going to do an example where it's necessary, but like there are more complicated problems where this is not just 1 times n plus something, where this is something where you can't always make the coefficients match up exactly, and then you need to do something slightly more complicated. Because the reason that this thing is divisible by n plus 300 is that this bit on its own is an integer whenever n is an integer. But if we had fractions in here, then this wouldn't be guaranteed to be an integer. So this wouldn't be guaranteed to be a multiple of n plus 300. But I think that's more complicated than what we need to worry about right now. The point is here that we get that n plus 300 is a factor of 510. And it's also bigger than 300. Now, I don't know. And I think that forces it to be 510. And the reason I say that is we know that the second biggest factor of 510, well, firstly, we know this because unless they messed up again, the solution should be unique. And so if it's possible for it to be 510, it has to be 510. So the second biggest factor of 510 is 510 over 2, which is 255. So this is bigger than square root of 510, but that doesn't mean that, like, it's not true that a number only has one factor bigger than the square root. The factors come in pairs, where one number in the pair is smaller than the square root and one number in the pair is bigger than the square root. So here 510 does have, yeah, but we do know that the second biggest factor is just 510 divided by the second smallest one, which is this 2 over here. So, if you were to write down all the factors, you've got 1 and 2, and that 1 is 1 times 500, and it's not 500, 510. And then 2 times 255, and this is smaller than 300. So all of the factors except the 510 is smaller than 300. But again, also, if they didn't mess up, then because this is a second round question where the answer has to be a 3-digit number, as soon as you know that it's possible for it to be 510, you know that it has to be 510, because otherwise the answer is not going to be unique. Although, as we saw like 10 minutes ago, sometimes they mess up. Anyway, so we've got that n is then 210. And then, yeah, that's just done, because then we know that this is a factor of this. And you can work out exactly how many soccer balls are in each box, but that's not what the question was asking. They just wanted to know what n is. And yeah, it's 210. Then we can go back to if you don't have questions about that, then we can go to the other one, but otherwise, yeah. Okay, good. This one is, okay. I don't want to do a whole lecture on what I mean by everything that I write, but what this does is, okay, so a permutation of the numbers from, in this case, 1 up to 13 is just some way of rearranging those numbers. And permutations can be broken down into cycles. So if we look at where the 1 goes, so the 1 goes to 6. And the 6, 1, 2, 3, 4, 5, 6 goes to 9. And the 9 goes to 1, 2, 3, 8, 9 goes to 10. And the 10 goes to 12. Yeah, 1. And then the 12 goes to, this is the 10, 11, 12. 12 goes to 5. 5 goes to 1, 2, 3, 4, 5 is 2. 2 goes to 1. Okay. So if we were to shuffle this twice, the ace would have become a 6. But then the 6, like the, although I've got this reversed, this is the inverse of this permutation. So actually, yeah, so what I actually meant to say is that the card that was in position 1 goes to position 2. And the way I'm going to notate this is the card that was in position 1 goes to position 2. And the card that was in position 2 goes to position 5. And the card that was in position 5 goes to position 12. And the I think that's right, yeah. 1, 2, 3, 4, 5. And the 5 goes to, yeah, position 12. And the card that was in position 12 goes to position 10. And the card that was in position 10 goes to position 9. And the card that was in position 9 goes to position 6. And then the 6 goes back to 1. So if I was to do this twice, the card that was in position 1 would go to position 2. And then because it was in position 2, it will then end up in position 1, 2, 3, 4, 5. So if I do this twice, the ace is now going to be in the 5th position because the first time we shuffle, it goes to the 2nd position, but everything that was in the 2nd position then ends up in the 5th position. And everything that was in the 5th position then ends up in the 12th position. And everything that was in the 12th position goes to the 10th position and so on. But this only accounts for 7 of the numbers. So we've got 6 more to deal with. So, okay, the card that was in position 3 goes to position 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, obviously. It's right at the end. And the card that was in position 13 goes to position 1, 2, 3, 4, 5, 6, 7. And the card that was in position 7 goes to position 3. And then this still isn't all the numbers. We know what happens to 1, 2, 3, so we need to look at what happens to 4. The card that was in position 4 stays in position 4. Then 5, 6, 7, 8 is the other one we have to deal with. 8, the card that was in position 8 goes to position 11. And the card that was in position 11 goes to position 1, 2, 3, 4, 5, 6, 7, 8. And then 9, 10, 11, 12, 13. Yeah. So this is what this shuffling machine does to the cards. It takes the card that was in position 1, puts it in position 2. It takes the card that was in position 2, puts it in position 5. It takes the card that was in position 5 and puts it in position 12. It takes that card and puts it in position 10, in position 9, in position 6. It moves the 3rd card to the 13th place, the 13th card to the 7th place, the 7th card to the 3rd place. It leaves the 4th card in the same position. It takes the card and it swaps the cards that were 8th and 11th. And if you do it twice, well, you're going to go 2 cards along this, 2 positions along this cycle. And if you do it 3 times, you're going to go 3 positions along this cycle. And so on. And the same thing, yeah, twice you're going to go, it's going to do that. Twice these 2 cards are going to swap around and then swap back. And so if you want everything to end up in the original order, well, how long is this cycle? 1, 2, 3, 4, 5, 6, 7. And this cycle has got a length of 3, and this one's got a length of 1, and this has got a length of 2. Yeah, so it's just the least common multiple of all the cycles. So we have to do it 7 times for this group of cards to end up back where they started. We have to do it a multiple of 3 times for this group of cards to end up back where they started. The 4 always just stays where it is, and we have to do it an even number of times for these 2 cards to end up back to where they started. And so we have to do this 42 times for all the cards to end up back where they started. But yeah, you break this permutation down into the cycles and then work out the least common multiple of the lengths of those cycles. I mean, I could go deeper into the theory of exactly how this works, but hopefully you understood what's going on here. The reason it breaks up into cycles in the first place is while we look at where the 1 goes, the card that was there goes into a new position. The card that was there goes into a new position. But you can't keep getting new positions forever. So eventually you're going to repeat, right? So you're going to end up that something goes back into position 1. And then the same thing. And so then you have a full cycle. And okay, you technically have to be a little bit careful because the way I worded that is not quite correct, because you could have something like this where you get that goes to a new position, goes to a new position, goes to a new position, and eventually you're going to get a repeat. And I sort of just claimed that you go back to the first one, but in principle, you could do something like this. You could repeat by going there. But the point is that all of these positions have got a unique thing that comes before them. So this one can't have 2 different predecessors because there's only 1 card that can end up there. You can't have 2 different cards that end up there. So the only place the repeat can be is back at the start. And so that's why you get cycles. But yeah, again, surprised that I don't know, maybe they're less obsessed about following the curriculum than I thought they were. I mean, I'm not complaining. These are much more interesting questions than you would get otherwise. But yeah, okay. Cool. Anyway, if there's no other questions you want to go through, then maybe it's a good time to stop. Oh, is it already next week? Yeah, I'll just do lots of past papers, I guess. Also, like the tricks for round 2 is that, with one notable exception, that like you don't have to be completely rigorous when you try to solve these questions, because that, as soon as you have a choice to be made, that the final answer shouldn't depend on what choice you make, because the final answer has to be like one number that's always correct. It's a fixed 3-digit number, again, with one notable exception where they messed up, this one. So with the exception of this one problem in the last 30 years, that there is a specific answer. And so if it looks like you've got a choice to make where this value could be this, or it could be this, or it could be this, just if you pick one and it works out, then that has to be the right answer. You don't have to then consider all the cases, because you know that unless they messed up when asking the question, you have to get the same answer every time. It's the same thing with like multiple choice. You know that one of those answers is correct. And so if you can eliminate the wrong answers, you don't have to understand why the right one, the remaining one, is actually correct. Because one of them has to be correct, and exactly one of them has to be correct. And it's the same thing here. You can cheat a little bit. I don't like doing that. I prefer actually being confident in the solutions. But I mean, if you pressed for time, then it's okay to not be rigorous in this context. Like, yeah, as soon as we got that this whole thing works out as long as n plus 300 divides 510, I went and explained why it doesn't have any factors. It only has one factor bigger than 300. But actually, because this is a second round question, like, that this has to be 510 because that is one of the possibilities. And you get the same answer every time because it has to be a fixed number at the end. And so you could have saved like 5 minutes by not having to think about maybe not 5 minutes, 30 seconds, by not having to stop and think, wait, does it have any other factors? It's like, okay, the obvious one has to work. How do you stop making dumb mistakes on the easy questions? I don't know. I just never did. I didn't have any specific strategy for it. Uh, I guess, yeah, just practice, and also practice with like one of the reasons people make a lot of mistakes on the arithmetic questions, for example, is that they just jump straight to using a calculator every time they have to do any arithmetic. So they don't have any practice with doing arithmetic and doing it quickly or accurately. And so as soon as you're not allowed a calculator, you're suddenly very bad at it. And anything else where you've got like these additional tools that help you, you get worse at doing it without those tools when you're not allowed to. I mean, like, obviously, this is the 21st century. It's like they should just let you bring a calculator into the paper, because like, who actually cares? What difference does it make? Most of these questions, the arithmetic, like, other than questions 1, 2, and 3, the arithmetic isn't the point of the question. Although it does then stop them from doing clever things with like difference of squares, if you can just plug the numbers into a calculator and get the answer without spotting the factorizations or whatever. But I don't know. They should change the rules. If the question can be solved trivially with a calculator or a protractor, then maybe it's a bad question. Anyway, you a bit over 70%. I actually don't know what the cutoffs have typically been. I think you can only really be confident you're going to be in the third round if you get like 90 and above. But 70 might be enough. I just don't actually know. 90 is usually definitely enough. Well, actually, the only way you can know for sure, absolutely 100%, is if you get 100%. Then you know that you're in the final. But obviously, that's, very few people do. I guess also you should like develop an intuition for what you expect the answer to be. Like, roughly how large is this thing? If I get something that's 5 digits long, is that reasonable? Is that a number that actually makes sense in this context? If they ask you to calculate a length and you get, 10 to the 26 meters, that's probably wrong, because that's like the width of the entire observable universe. Or if you want to calculate a mass and you get, 10 to 100 kilograms, that's more than all the matter in the entire universe. It's probably wrong. So just having like some kind of intuition for what, roughly what the answer should be, then it's easier to spot, if you've made a mistake. The Earth is like 10 to the 25 kilograms, the moon is 10 to the 22, the atmosphere is 10 to the 19. So if you're getting numbers that big, it's not the mass of a soccer ball. It's not even the mass of an elephant. It's the mass of, what's an elephant weigh? 10 tons? So it's the mass of, 10 to the 21 elephants. Like, yeah. I mean, okay, usually it's not going to be that extreme, the difference between what you get and what you expected. But, like, yeah. I guess it's called number sense or whatever. A rough idea of what you think, expect the answer to be. Well, I guess that means that there's no more. Um, what year was this from, actually? Again, I'm like surprised that they ask questions that are this far out of the standard curriculum. Like, they've become a bit more obsessed with keeping it approachable for all high school students. Oh well. Anyway, if there's no other questions or comments, then yeah, it's probably a good time to stop, and then you can do some more past papers and hopefully do very well on Thursday. That was 2014. Yeah, okay, that makes sense. 2014. I don't know exactly which, like they've becoming easier over the years, or maybe I've just become better at it over the years. I'm not sure which one is more accurate. Yeah. Oh, okay. So the soccer ball one was the final question. And that's already, like, that's much simpler than, um, like, as far as find all values of n such that this divided by this is an integer, this isn't even an especially, like, difficult example of, like, it's simpler than it could have been. Yeah, when you put this in, I thought this was like question 12 or so. So if this was question 20 already in 2014, then they were already not doing horrible things. Okay. Another question. Let's look at it. The roots of 64x cubed minus, oh goodness, that horrible thing, or an arithmetic progression. Lol, I don't know. I mean, the thing with all of the, like with the first thing that comes to mind is like I can work out what the sum of all the roots are, but that's different from knowing. Guess it somehow. I mean, like, okay, so things that might work is either there's some obvious roots and so you can just solve the equation and work it all out, or I don't know. Oh, he did factorize. Okay, cool. Like 1 isn't a root, so they're not that nice to you. But like, if you do want rational roots of this thing, so there is the rational root theorem, or whatever it's typically called, that if you have a polynomial that starts with a times x to the n plus a whole bunch of other stuff plus something times x plus b, and all of these are integers, integer coefficients, and this is equal to 0, then if x is rational, so if let's say I've already used n for the degree now, let's call that a d for degree. If m over n is a solution where m and n are relatively prime, then m divides is a factor of the constant term of the polynomial, and n is a factor of the leading coefficient. And so you can like write out what all the possibilities are for like the rational roots. So maybe, we could expect 1 could be a solution, 3 could be, 5 could be, 15 could be, 1 over 2 could be, 3 over 2 could be, 5 over 2 could be, but that's not going to be pleasant. Let's see, is there anything else here that stands out? I mean, probably the 64 being 4 cubed makes me think that it's going to be 4x plus something, 4x plus something. Like, it's not guaranteed to be this, but it's not unreasonable that it would look like this. And then what? We know that whatever these things are, so it could be like 1, 3, and 5 maybe. So it could be like -1, -3, -5. If I had to guess, that might be the factorization. 9. It's not. It might be 16 times 9 is 144. Well, okay, that's stupid. I think this is just a factorization, but like I've got nothing to justify that other than, wouldn't it be nice if it was? The 135 also is because I knew the roots are in arithmetic progression, like they said, so I made these in, it's going to be 1/4, 3/4, 5/4 as the roots in this case. Like, if all these coefficients of the x are the same, then these things should also be an arithmetic progression because they're just four times numbers in some arithmetic progression. They're not just like, okay, we want factors of 15, 135. So, if I had to guess a factorization, this is what I'd guess, but I didn't actually do any factorizing here. I was just like, okay, cool. Maybe the nicest way this could possibly factorize is this. And it seems to actually work. The 64 ends up being right at the start. The 15's right. And I've already checked that if you take 4 times 4 times 1 plus 3 plus 5, you do get 144. And then I guess the 92 is supposed to be 4 times 3 plus 15 plus 5. It's 21. No, 3. Oh, no, no. Yeah, 4 times 3 plus 5 plus 15, 23. Yeah, is 92. This is the factorization. That's bizarre. Difference between the largest and smallest roots is then 5 over 4 minus 1 over 4, which is just 1. I wonder if there's a way to do this without doing this. Hmm. This is definitely the easiest way if you spot this, but like again, this is I don't want to encourage. Well, I don't know. Maybe I do want to encourage this method of factorizing, but usually it doesn't work out like this. Usually the factors don't split, nice and evenly between all three of the brackets. Because I mean, there's other ways of getting a 64. It could be 1, 1, and 64. It could be 1, 2, and 32. It could be 2, 2, and 16. It could be a lot of things. It's maybe a bit more reasonable that they're all roughly equal because you do want the roots to be an arithmetic progression. So you do want this to be, roughly like the 1, 1, and 64 is definitely not going to work because then you're going to have an integer, and some integer over 64. And like for that to be an integer, then the other part of that would have to be very big. So like maybe the fact that they're an arithmetic progression means that you're more likely to get this even splitting. But like in general, if you're trying to factorize polynomials, you're not going to get like this is a very rare thing to happen. So it's the nicest possible thing that can happen. And so I guess, yeah, if you, yeah, maybe engage in wishful thinking, then this is not that hard to come up with, but this is not a very, principled method. There's no reason to expect it to look like this other than, okay, guys, so let's look at something like, let's just use this example, 64x cubed. What was it? Minus 144x squared. X squared plus 92x minus 15. And let's say we want a rational root of this thing. So let's say that we know m over n is a solution, where these are integers and the GCD is 1. 1, n is not equal to 0, and m and n are integers. This is a rational number in its simplest form. So now just substitute this in, and you're going to have 64 times m cubed over n cubed minus 144 times m squared over n squared plus 92 m over n minus 15 equals 0. Now let's multiply by n cubed to get rid of all of the denominators. And so we're going to have 64 m cubed minus 144 m squared n plus 92 mn squared minus 15 n cubed is 0. Okay. And so now if we look at this, these terms over here are all divisible by m, and 0 is divisible by m. And so we know that 15n cubed is equal, 15n cubed is m times some number that is an integer. And so we know that m divides 15n cubed. Because, you know, we can just take the 15n cubed across and you can factor out the m from everything that's left. But m and n, the GCD is 1. And so this means that m must divide 15 because it's got no factors in common with the n cubed. And we can do the same thing. How did this page end up at the bottom here? I don't even know. We can do the same thing with 64m cubed. 64m cubed is equal to n times something because all of these things have got an n in them. And again, so this means that n divides 64m cubed. And so because n and m have got no factors in common, this means that n divides 64. And so for any possible rational number that's a solution, the numerator has to divide 15, this constant term, and the denominator has to divide 64, the leading coefficient. And if you work this out in general with any polynomial, you'll come to the same conclusion. You're going to have if you have a polynomial of integer coefficients, so p has integer coefficients, and p of m over n equals 0, where GCD m and n is 1, blah, 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 blah. Scroll up back here. Yeah. So the n divides, so we've got from this thing, we've got 64 m cubed is, well, it's n times 144 m squared minus 92 mn plus 15 n squared, but it's n times something. So it's this equation, but take everything across except the 64 m cubed. And so we've got that n is a factor of this. So it has to be a factor of this. So n is a factor of 64 m cubed. And then we use we're assuming that the fraction is in its simplest form. The GCD of m and n is 1. And so that means that the n divides the 64. And yeah, so this happens completely in general. So, you know, with the same assumptions, n is not 0, m and n are integers. A lot of extra stuff, but if this is a fraction in its lowest terms, then m divides the constant term. Constant term. And n divides the leading coefficient. And they can both be negative. It's not just positive factors of those numbers that work. Now, this doesn't give you all of the roots, it just gives you all of the possible rational roots. It's also not true that it's not true that every factor of the constant term and every factor of the leading coefficient is going to be a solution. It's just that these are the only possible solutions. It might be that none of these actually work. In a lot of questions, they're especially nice to you and just 1 or minus 1 ends up being a solution, and then you can factor out either x minus 1 or x plus 1. Sometimes they're a little bit more mean and you have to go to 2 or minus 2. If they're very mean, you end up with actual fractions. Any other random equations? Like, no. If it's a quadratic, you've got the quadratic formula. If you've got a cubic, then usually some rational number is a solution, so you can factorize it out. And then you've got, that factor times a quadratic, and then you can use the quadratic formula for the other factor to find the rest of the roots. The other thing that comes up quite commonly is that mn plus something m plus something n that we did earlier equals something. So like one way that they've asked us in the past is they had something like 1 over m plus 3 over n maybe is say, why is calculus never tested? Because the South African schools are useless and you don't learn it until like grade 12, and even then they teach it very badly. And yeah, at the IMO, the calculus is never necessary, and so if this is supposed to be, the first part of the selection process for the IMO, then there's no point in, covering topics that are never going to be used later on. I think it's mostly just because it's taught quite late in school and not very well. Let's say this was 7. I don't know if this has any solutions, but this is one variant where this thing like shows up sometimes. So if you multiplied by mn, you'd have n plus 3m equals 7mn. And so the trick here is again that we're going to multiply by 7. And so we're going to have 49mn minus 21m minus 7n equals 0. And then we can factorize this as 7m minus 7, I guess. Oh no, sorry, minus 1. 7n minus 3 equals 3. This is looking like something that doesn't have solutions, but then, yeah, then you try all the possible factors. So like questions that look like this always end up being something times something equals some fixed number. If you're very lucky, this fixed number is 0, so that one of these things has to be 0. If you're unlucky, then, well, this still only has a finite number of factors, so there's only finitely many possibilities to try. And in this case, it looks like none of them work, so I should have picked a different number there where this actually has solutions, but this is the procedure for this kind of question. Other than that, yeah, I don't know, stuff that typically comes up. One factorization that you might not know that is sometimes useful. I multiplied by the 7 so that I can... It's always just useful to multiply by whatever this coefficient is, then this is guaranteed to be able to factorize. Whereas over here, like I can't really do anything at the moment. If I had 7m minus something, n minus something, there's nothing I can pick there to make these coefficients. Like this would have to be a 1, but this would have to be a 3 over 7 is equal to 3 over 7. But, if I first multiply by this, I'm guaranteed that I'm going to that I only need integers in this factorization. And when these are all integers, then, then I know that this is an integer times an integer is 3. And so these are both factors of 3. It's, this is 1 and this is 3, or this is 3 and this is 1, or this is minus 1 and this is minus 3, or this is minus 3 and this is minus 1. You end up with some fixed finite number of possibilities to consider. But yeah, with this kind of thing, it's almost always useful to first multiply by whatever coefficient happens to be there, and then you're guaranteed that you can get a factorization that just uses integers. Or not a factorization, because this isn't like a factorization of this thing. Because it's not that this is equal to this, it's just that I can manipulate this to look like this equals something. The other thing that's sometimes useful that you might not know is this factorization. X cubed plus y cubed plus z cubed minus 3xyz has got a nice factorization. It's x plus y plus z, x squared plus y squared plus z squared minus xy minus yz minus zx. The other one that's useful that you also might not know, I think it's something like a squared b squared, 2a squared b squared plus 2b squared c squared plus 2c squared a squared. This is useful less often, but it is not completely useless. Come. Okay. Unfortunately, it is a holiday in the Netherlands, and so Amazon is not delivering yesterday or today. And so the new batteries I ordered for this pen are only arriving tomorrow. And we don't have the nice thing that South Africa does. So if it's a holiday on a Sunday here, you don't get the Monday off. At least not automatically. Yeah, I'm in the Netherlands. This is A plus B plus C, A plus B minus C, A minus B plus C, minus A plus B plus C. Or something like that. These might have to be 4s or something. I think it's like this that it works, but it's possible I'm wrong. Let's see, we're gonna have the A's and B's. We're going to have I don't know. I don't want to check it. Yeah, it's quite horrible, but actually, the only time it's even been vaguely relevant, actually, is I think IMO 2012 problem 4 was based on this identity. And it was a functional equation, so you don't even actually need to know this identity. Because way back in the day, the way that you come up with functional equations is you start with some identity, the more horrible the better. And then you add some, you add some random f's into the problem statement. Yeah. Oh, actually, it was a slightly modified version of this without the squares on it. So this is, yeah, this is the IMO problem that was dreamed up by a certain Liam Baker that started by taking this thing and yeah, so here I think you end up with like f of x equals x squared is a solution, basically because of this identity. Am I right about that? Because we're going to have, I don't know. Yeah, I think this factorization is right, but it's not something that's going to show up in the second round, hopefully. The other one that's actually much more useful than that you might not know is the x to the 4 plus 4y to the 4 is x squared plus 2y squared squared minus 4x squared y squared. And so that's now a difference of two squares, and so this ends up as being x squared minus 2xy plus 2y squared x squared plus 2xy plus 2y squared. Other than that, yeah, nothing comes to mind for useful stuff to know to solve equations. I mean, I assume you know how to solve systems of linear equations, and I assume you know how the quadratic formula. Cool. Anything else? Okay, cool. Maybe it's a good place to stop. I'll good luck for Thursday. And yeah, have a good evening.